The law of universal gravitation truly is universal. So for that reason, we can use it to tackle some pretty big questions. That's what I'm going to do for the remainder here of this unit on gravitation. In doing so, this is my opportunity to throw as much astronomy at you as I possibly can. So then therefore, I'm going to take full advantage of that for the remainder of this unit on gravitation. However, I'm going to start off rather simple and straightforward. Let me introduce you to the following problem. Let's examine what happens when an artificial satellite orbits the Earth. Copy down the following problem into your notes. Derive an expression for the period of an artificial satellite orbiting the Earth in uniform circular motion, and then later on we'll take a look at an application. We'll find the altitude of what is called a geosynchronous satellite. Well, let's derive the expression that we're looking for first. In doing so, essentially all that you're going to see here is a brief repeat of Kepler's third law. Kepler's laws of planetary motion, of course, are specifically applied to the planets as they orbit the sun, but the basic physics describes anything that's orbiting anything else, such as, for example, what happens as an artificial satellite orbits the Earth. Okay, so let's begin the problem in the following way. Okay, right here we'll say is the Earth, and then right here is the mass of the Earth, m sub e. Remember from an earlier lecture that we know what that number is equal to. The mass of the Earth is 6 times 10 to the 24 kilograms. Okay, now before I go any further, we also, of course, have capital G. We now know that it was first measured during the Cavendish experiment that I explained in an earlier lecture. Right here are the units associated with that number. Okay, and then right here we'll say is our satellite, like so, of mass m in uniform circular motion about the Earth. Okay, now the distance between the satellite and the center of the Earth, we're going to say here is small r. And now we just set up F equals ma. According to Newton, there's only one force exerted upon the satellite, and that's the force of gravity. So capital G times the mass of the Earth times the mass of the satellite divided by distance squared. This then equals mass times acceleration. The acceleration is a centripetal acceleration, however, inwards towards the center of the orbital circle, which is inwards towards the center of the Earth. So then therefore we'll write the net force here as the centripetal force, mv squared over r. This is essentially the starting point for any situation involving an object orbiting another in uniform circular motion, where we treat this object here as stationary. Okay, now the same things always cancel. The mass of the satellite in this case cancels out, as does one of the distances r, like so. And then at this point we have the following expression. Like so. And now we make the following substitution for the speed v. The speed v is equal to circumference divided by the period. So let's go ahead and plug that in, and when we do, we square all the terms. That then gives us the following. So first of all, the left-hand side of the expression, and now on the right-hand side, we have a v squared, which is like so. And now let's just cross multiply and solve for t squared. So when I cross multiply and solve for t squared, I then end up with this expression here. You should recognize this expression from one of the earlier lectures, specifically the unification problem involving Kepler's third law, because this is Kepler's third law. So what I've done here is I've just done a quick re-derivation of something that we have already seen. The only difference, of course, is the mass of the object that is being orbited. In this case, it's the mass of the Earth. But Kepler's laws of planetary motion are universal in the sense that they apply to anything that's orbiting anything else, such as, for example, this situation here involving an artificial satellite orbiting the Earth. And now mathematically, notice how this expression behaves. If you increase the distance r on the diagram above, you then therefore increase the orbital period. So the further and further that the artificial satellite is from the Earth, the longer and longer it takes for it to orbit the Earth. If you're talking about an object in what is called low Earth orbit, like the International Space Station, well, the International Space Station orbits at an altitude of a couple of 100 miles above the Earth. It typically takes about 90 minutes or so for one orbit to occur. That is typical of what is called low Earth orbit. And now let's take a look at a specific application of this expression. Okay, the application that we'll look at here, and I'm just, by the way, going to rewrite the expression up here on the top board. Let's just go ahead and write this like so. Okay, so the application that we're going to take a look at here for the second portion of the problem is what's called a geosynchronous satellite. A geosynchronous satellite is in what is called geosynchronous orbit. Okay, let me introduce you to a geosynchronous satellite, a geosynchronous orbit, in the following manner. Some of you, I'm sure, for example, perhaps have satellite TV, like DirecTV or Dish Network or something like that. Then, of course, in order to receive the television signal, you have a satellite dish up on your roof or on your balcony, and that then receives the signal from the satellite in the sky. Do you ever have to go outside, however, at different times of the day or different times of the year and reposition your satellite dish in order to pick up the signal? No. Your satellite dish is always pointed at the same point in the sky 24 hours per day, 365 days per year. The reason for that is because the communications satellite that you're receiving the signal from is in what is called geosynchronous orbit. In geosynchronous orbit, relative to the surface of the Earth, the position of the satellite in the sky never changes. This then means that the satellite must be orbiting the Earth at some altitude above the Earth's surface, specifically above the equator. The situation looks like this. Okay, now let me just go ahead and draw the situation here in profile on the lower board. Let me now go ahead and first of all draw the Earth like so. Okay, now in profile, right here is the Earth's equator, center of the Earth. So there's M sub E. And then right here is the North Pole, and right here is the South Pole. And now I'm going to go ahead and position the satellite here with mass M, and then the orbital circle of the satellite has a radius associated with it. That's this distance here. However, as the Earth rotates, relative to the surface of the Earth, the position of the satellite in the sky never changes. So then therefore, if my left hand is the surface of the Earth, and my right hand is the satellite, then the situation looks like this. Such that, for example, if you were, say, standing right here at the equator, you would then see the satellite straight overhead 24 hours per day, 365 days per year. Therefore, the satellite is in geosynchronous orbit. This then means that the orbital period of the satellite, of course, has to match the rotational period of the Earth. So the orbital period of the satellite is 24 hours. That's 1 day. That's equal to 86,400 seconds. So now what I'm going to do is I'm going to use Kepler's third law on the board above, rather, and I'm going to solve for small r. Once I have small r, I'm going to take that value and subtract from it the radius of the Earth. That will then give us the altitude above the ground. So let's go ahead and jump up to the top board, and let's go ahead and solve for small r. Okay, so to solve for small r, let's first of all cross multiply this stuff to the other side of the expression and get r cubed by itself. So now solving for r cubed, that then gives us this when you do the cross multiplying. And now what we do is we take the cubed root of both sides. When I take the cubed root of both sides, on the right-hand side, what we have are these terms in parentheses raised to the 1/3 power. And now I have to plug in all of my numbers. So first of all, we have capital G, 6.67 times 10 to the minus 11, then times the mass of the Earth, 6 times 10 to the 24, and then multiply by 86,400 seconds squared. Take all of that and then divide it by 4 pi squared. There we go, like so. And then raise the whole thing to the 1/3 power. That's taking the cubed root. And when you do, you end up with quite a big distance. It's 4.2 times 10 to the 7th meters, but that's not the altitude above the ground. The altitude above the ground, this distance here, by the way, is typically referred to as h. That distance there is equal to the small r that we just found, but now we have to subtract from it the radius of the Earth. Recall that the radius of the Earth is a known quantity since the time of Eratosthenes. It's 6.4 times 10 to the 6 meters. So the altitude above the ground is going to be small r minus the radius of the Earth. This is still going to be quite a large distance. This is well above low Earth orbit. So if I now subtract from small r the radius of the Earth like so, I then end up with about 3.6 times 10 to the 7th meters. That's about 36,000 kilometers. That's about 1/10 of the distance from the Earth to the Moon, This is geosynchronous orbit. So when you position a satellite in geosynchronous orbit relative to the surface of the Earth, its position in the sky never changes. But it does have to be positioned above the equator. If you didn't position it above the equator and it orbited on an angle, for example, like so, then its position in the sky would change relative to the surface of the Earth. It must be above the equator in order for it to be in geosynchronous orbit. Now, for those of you that do have satellite TV, in which direction is your satellite dish pointed? It's pointed towards the southeast. And the reason for that is because the communications satellite for both DirecTV and Dish Network, it's the same satellite, by the way. The communications satellite for both of those networks is positioned 36,000 kilometers above the equator south of Texas, which is basically the middle of the country. So here on the West Coast, your satellite dish is then therefore pointed slightly to the southeast for that reason. In addition to communications satellites being in geosynchronous orbit, all weather satellites are also in geosynchronous orbit. Because when you watch the weather on the news, for example, and you watch a time lapse of the weather over the course of several hours, the perspective of the camera never changes. In other words, relative to the surface of the Earth, the position of the satellite in the sky never changes, 24 hours per day, 365 days per year. That's because it's in geosynchronous orbit. So when you watch the weather on the news, because the satellite is way out there, 36,000 kilometers above the ground, they can then use their camera, and it's basically a telescope, by the way, to look very closely at the weather, say, over Los Angeles, and then they can pull back and look at the weather over California, and then they can pull back even further and look at the weather over the northern hemisphere. And the reason for that is because the satellite itself is positioned so far above the Earth's equator at a distance of 36,000 kilometers. So a geosynchronous satellite in geosynchronous orbit is a nice application of a basic orbital problem involving an artificial satellite. Okay, moving from this point forward, we're going to start to move way out into the universe. We'll do that in the next series of lectures.